compounding and molecular structure. Okay? So good morning to everyone. So can anyone send me the message which topic we had discussed in the last class? Any one of you? Okay, parameters related to bonds. Very good. So that's where we have discussed about the parameters, as you told. Very good. So that's where we have discussed about bond length. Right? Then we have discussed about bond length. And then it is related to bond order. It is related to bond order. Then we have discussed about bond angle. Before that, we have discussed about bond enthalpy. Right? So that's where we have discussed about these things. Bond angle, yes, it is a separate one, but these three are related to each other. Right? So that's where when I am talking about bond length and bond order, they are inversely related. When I am talking about bond length and bond enthalpy, once again they are inversely related. So what I mean to tell you is, if I consider this one as BL, this one as BO, and this one as BE, now I can tell that bond length is inversely proportional to bond order and bond enthalpy. Bond order and bond enthalpy. Okay? Bond order and bond enthalpy, in that case, they should be directly related to each other. They should be directly related to each other. As the bond order increases, bond enthalpy will also increase. Right? So amount of energy required to break the bond will increase as the number of bond will increase. That's where bond order. Number of interaction between the element. Okay? All of you have understood? So yes, Sapa, good morning. Fine? So that's where we have some of the parameters. Then we have discussed about bond angle by taking the example of water. And I told, with respect to VSEPR theory, we are going to discuss in detail. Okay? Once again, I will come back to whatever I have told. It is applicable for covalent compounds. It will be applicable for covalent compounds. Same way, we will come to next important one. I will mention this one as very important. Another important parameter related to covalent compounds. Okay? So that is dipole moment. That is nothing but dipole moment. Now when I am talking about dipole moment, right? So with respect to a covalent bond, for example, I have the chlorine molecule where two chlorine, they are attached to each other by a covalent bond. Two chlorine atoms, they are interacting with each other to form the chlorine molecule. Same logic is applicable if I am talking about hydrogen molecule. So where hydrogen interacting with each other. So what I mean to tell here is, whatever I have taken the example or whatever examples I have written on the board, they are all examples where same type of element they are bonding with each other. All of you will agree? If I take chlorine, chlorine is bonded with chlorine to form the Cl2. Hydrogen is bonded to hydrogen to form the H2. Same way, if I take the ozone, O3, where three ozones, they will be attached to each other. Three oxygen atoms, they are attached to each other. That's where we have the ozone. So same type of element. So what I mean to tell here is, whatever I have written, it is a molecule where same type of elements are involved in the interaction. It's not a compound. It's not a compound. Molecule is a broad term, right? But compound is very specific. So they are not the examples for the compounds. Why? Because all of them, they are having same type of element. All of you have understood? So if I talk about chlorine, we know that this chlorine has invested one electron and another chlorine has invested one electron. That's where covalent bond has been formed. Same logic is applicable here. So one hydrogen has invested one electron, another hydrogen has invested another electron. So that's where we have the covalent bond between the hydrogen atom. Same way between the oxygen atoms. Only thing here is, in case of the ozone, there will be presence of coordinate covalent bond. But anyway, we are not going to discuss that one. We have already discussed that one, but for time being, focus on whatever I am talking, that there will be sharing of electrons by the element. Therefore, it is a covalent bond. Right? All of you have understood? When I am talking about chlorine, both are electronegative, but no one is going to dominate over the other. From few days I was not feeling well, sir, so I don't attend the class, sir. Okay, it's fine, Vishwas, but you should be very careful, take care, okay? And after day after tomorrow onwards, we'll be having exam also, okay, Vishwas? Okay, Rakesh, I will give another example. So when I am talking about chlorine, there will be sharing of electron, hydrogen, there will be sharing of electron. So what I mean to tell you is, any element you take, sir, give another example. Yes, any other example if I want to take, for example, fluorine, where two fluorine, they are sharing the electron. And all of us, we know fluorine is highly electronegative. But now, if you see these examples, still electrons will not be taken or attracted by any of the element, because both are equally potent, because both are same element. All of you have understood? Right? So since both are same element, these electrons will not be attracted by this fluorine or will not be attracted by this fluorine, because both are equally potent. Okay? So what I mean to tell you is, electron 1, electron 2. So electron 1, anyway, it belongs to fluorine 1. Electron 2 belongs to fluorine 2. But both have been invested. Yes, Dikshit, very good morning. So both have been invested for the bond formation. Now electron 2 will not be pulled towards the fluorine. Electron 1 will not be pulled towards the another fluorine, because both are same element. Both are equally potent. Right? So that's where dipole moment. Now listen to me carefully. Dipole moment. Whatever I am telling, they are not applicable for a molecule having same type of element. Dipole moment is not applicable for the molecules having same elements. All of you have understood? So that's where we have the one of the main clause. Dipole moment will not be applicable for those molecules containing same elements. Any doubts in this? Okay? And due to that, now I can tell chlorine is a gaseous molecule at room temperature. Hydrogen is a gaseous molecule. Ozone is a gaseous molecule. Fluorine is a gaseous molecule. So what I mean to tell you is, All these molecules, whatever I have mentioned, most of them they are gaseous in nature. Most of them they are gaseous in nature. Fine. So all of you have understood? Sanjay? Okay. So shall we move to the next one? So these are some of the examples, but for here there is no application or there is no question of dipole moment, because dipole moment is not applicable for those molecules which are having same type of element. Yes, Rakesh. In that case, I will take HCl, hydrochloric acid. HCl, hydrochloric acid. Now, all of us we know that when I am talking about hydrochloric acid, there is a presence of covalent bond. There is a presence of covalent bond between the hydrogen and chlorine. Some students they will get confused. They think that it is an ionic compound. No. Cl is a covalent compound. There is a presence of covalent bond between hydrogen and chlorine. However, all of us we know that chlorine is highly electronegative. So therefore, hydrogen will behave as electropositive in this example. Since chlorine is highly electronegative, since it is a halogen, therefore hydrogen will behave as an electropositive element in this case. Okay? Now, all of us we know that electronegative. What do you mean by electronegativity? It is nothing but capacity of an element. Electronegativity means capacity of an element to attract the electron. Listen to me carefully. Already we have discussed this one. So electronegativity means it is the capacity of an element to attract the electron in a covalent bond towards itself. It is nothing but electronegativity. And chlorine is an electronegative element. Yes, Sanjay, it is the potency or capacity of element to attract the electron towards itself in a covalent bond. Fine? So that's why chlorine is an electronegative. Now, generally we will draw like this to make you understand. I will tell that electrons will be present like this. Although this electron, I will give different shading. Although this electron belongs to hydrogen, but still it is pushed towards the chlorine. It is near to the chlorine. Please remember, it's not completely donated to chlorine, but it is pushed near to the chlorine because chlorine has attracted the electron of the hydrogen. So therefore, and that's where electronegative element comes. And due to that, there will be formation of partial negative charge on the chlorine, partial positive charge on the hydrogen. In this case, dipole moment is applicable. In this case, dipole moment is applicable. All of you have understood? For HCl, dipole moment is applicable, but it should be a covalent compound. Any compound where electronegative and electropositive elements are involved in bond formation, in those compound dipole moment will be present. Observe this statement. Any compound, I am not telling molecule, I am specifying compound. Any compounds having covalent bond, having covalent bond between electronegative and electropositive elements. Electropositive elements. We can tell like this, or which differs in their electronegativity. That is also fine. Which differs in their electronegativity. That is also fine. I am not mentioning highly electronegative, highly electropositive. I am just mentioning electronegative and electropositive elements will have the dipole moment. Will have the dipole moments. Will have the dipole moments. All of you have understood? So that's where we have the dipole moment, where it can be observed. Which type of compound it will be observed? So it will be observed in those compounds which are having covalent bond. Now specifying covalent bond, that means dipole moment is not applicable for ionic compounds and all. It's applicable for covalent compounds. So compounds having covalent bond between electronegative and electropositive. Okay, so elements will have dipole moments. Fine. So those type of compound will have the dipole moments, where there will be formation of partial negative, partial positive charge. See, for example, if I take NaCl, all of us we know that it is an ionic compound, right? So where chlorine will have the negative charge, sodium will have the positive charge. I am not mentioning partial positive, partial negative. I am mentioning positive and negative. Okay, that's where the difference between ions and with respect to dipole moment. Fine. So here we cannot mention with negative sign. You have to mention delta negative, delta positive. That shows that partial positive, partial negative. Fine. Now, since electron has been pushed towards the chlorine, we can mention this one like this, where positivity is present towards the hydrogen, since electron is pushed towards the chlorine. That's how the dipole moment can be denoted. All of you have understood? So positive is slightly positive. On the arrow it looks like positive, because hydrogen will be having partial positive charge, because electron is pushed towards the chlorine. So that's what that arrow talks about. To which direction electron is getting moved. That's what this arrow talks about. Any doubts in this? So which type of compound will have the dipole moment? Those compounds which are having elements with differs in their electronegativity. So those type of compounds will form the covalent compound, and those type of compound will show the dipole moment. All of you have understood? Any doubts? Shall I move to the next? In dipole moment only. Shall I move to the next? Okay. So I have taken the example of HCl. Now this is where we can find in which type of compound dipole moment will be observed, and in which type of compound dipole moment will not be present. So that's what we have discussed. Okay. So we will come to the next one in a dipole moment only. So we have a formula. We have a formula where dipole moment will be equals to, dipole moment will be equals to charge into distance. Charge into distance between the charges. Charge into distance between the charges. Between the charges. Okay. So that's where we have the equation for dipole moment. That's where we have the equation for dipole moment. Charge into distance between the charges, or I can tell, okay, distance between the charge, that will be the better word. Okay, all of you have understood? So normally charge will be having the symbol as Q, and distance or separation of charge will be mentioned as R. Okay, so Q and R. And the dipole moment, symbolically we can mention it as nu. Symbolically we can mention it as nu. All of you have understood? So that's where we have the dipole moment. Mu is equal to charge into distance between the charges. Or we can tell that separation, distance of separation of these charges. So that's where we have the dipole moment. Right? All of you have understood? Now, naturally, unit for the charge will be Coulomb. Unit for the charge will be Coulomb. That is capital C. Unit for the charge will be Coulomb. And distance, that is nothing but length. That means it should be meter. Symbol is M. Symbol is M. So therefore, unit for dipole moment will be Coulomb meter. Unit for dipole moment will be Coulomb meter. All of you have understood? Coulomb meter. Okay? But still, based on one of the scientists' name, to show the gratitude for his contribution, people will go with another unit for the dipole moment, which is called as Debye units. Which is called as Debye units, capital D. Which is nothing but Debye units, capital D will be the symbol. Charge into distance, that is nothing but Coulomb meter. Fine. So Coulomb meter. Coulomb is the unit for the charge, and distance it will be meter. So therefore Coulomb meter. But to show the gratitude of a scientist towards the science, that's why Debye is the person's name. So we can go with the Debye units. Okay, it will be gone with Debye units, dipole moment. Now we have a conversion factor. We have a conversion factor between Debye units and Coulomb meter. So 1 Debye unit is equal to 3.33 into 10 to the power of minus 30 Coulomb meter. 1 Debye unit is equal to 3.33 into 10 to the power of minus 30 Coulomb meter. So that's where we have the conversion factor. Okay? You should remember, so it's fine. Otherwise, you should remember Coulomb meter, definition of dipole moment. So that and all you should remember. If I want to define the dipole moment, now I can define. Dipole moment is the charge and distance between the separation of these charges in a covalent compound. In a covalent compound, I can tell that dipole moment is the multiple of or product of, better word is product of charge and distance of separation. Charge and distance of separation of these charges in a covalent compounds. In a covalent compounds. All of you have understood? So that's where I can define the dipole moment now based on the equation. I can define the dipole moment. All of you have understood? Any doubts? Okay? So shall we move to the next one? I will explain with some of the examples for dipole moment. All of you have understood? So remember about Debye units and why Coulomb meter. Then remember about the equation for the dipole moment. And based on that we can define the dipole moment. And what is compulsion here? For molecules to have the dipole moment, there should be involvement of two different elements with different electronegativities. Then only we can observe the dipole moment. Fine? All of you have understood? Okay, I will take the examples from your textbook only. For example, I have boron trifluoride. I have a compound called as boron trifluoride. Now, if I see this particular compound, in the name itself it is there, boron, B, then trifluoride, that is F3. So, boron trifluoride. Okay. Now, boron belongs to group 13. Boron belongs to group 13. How many valence electrons? Boron belongs to group 13. Okay, I think Sanjay, it has been displayed in the group. Have you received? You are in the group? I think it has been sent in the group. Okay. So, with respect to boron, group 13, how many valence electron? Any one of you? How many valence electron in boron? Can any one of you tell me? Yes, very good. It will be 3 valence electron because it is a group 13 element. So 1, 2, 3. As far as possible. Right? Lewis symbol. That's what? As far as possible. Okay? Hagadre. When I am talking about trifluoride, that means 3 fluorines, they are present here. So 3 fluorine, they are present here. That's where we have the boron trifluoride. Okay? Fine? Hagadre. When I am talking about boron trifluoride, among these boron and fluorine, which is electronegative? Just send me the symbol of the element. Which is more electronegative among boron and fluorine? Any one of you? Okay, according to Rohan, it is boron which is electronegative. Any other answer? Okay, Ganavi, boron. Shashank, fluorine. Pooja, boron. Okay, so any other answers? Okay, whoever has written fluorine, like Harshita, Shuchita and all, very good. How come boron? So many times I have told. Yes, now you people are writing. It should be fluorine. Fluorine is the big boss when it comes to electronegativity. No one can beat the fluorine with respect to electronegativity. Okay? So, fluorine is highly electronegative. So, therefore, if I am talking about the covalent bond, naturally there will be presence of dipole moment like this. There will be presence of dipole moment like this. All of you have understood? So, boron will be having positivity, partial positivity, and fluorine will be having partial negativity due to the movement of electrons. But observe here carefully, observe it carefully. But when I take the molecule, net dipole moment of boron trifluoride is 0. Net dipole moment of boron trifluoride is 0 as a whole. As a 3 bonds, if I consider all together, then it will be 0. Please remember, if I consider only one, then I can see there is a dipole moment. But when I consider the whole 3, net dipole moment, net means total. Okay, what is left over considering all the 3? Because when I am talking about BF3, I cannot focus on only one boron and fluorine bonding. I have to consider all the 3. So therefore, net dipole moment is 0. Why net dipole moment is 0? Because all the bonds, they are equal and opposite, because they are present at each three corners. So therefore, since their dipole moments are equal and opposite, net dipole moment will become 0. Net dipole moment will become 0 because boron trifluoride will have the trigonal planar structure. Anyway, with respect to VSEPR theory, we are going to discuss 0. That is because it is having trigonal planar structure. So therefore, all the bonds will be equal and opposite. So therefore, they are going to cancel each other's dipole moment. So therefore, net dipole moment of boron trifluoride will become 0. All of you have understood? Any doubts? The reason you have understood why net dipole moment of boron trifluoride is 0? Since it is having trigonal planar structure. That may you write or may not be, but this is important. So dipole moment of boron and fluorine bonding is equal and opposite. That word is important. So therefore, net dipole moment will be 0. Okay? Any doubts in this? Any doubts? That is with respect to boron trifluoride. If you have any doubts, you can ask. Okay, done. Yes, Vishwas. Now we will come, I will give another example. Beryllium fluoride. What should be the symbol? BeF2. Beryllium. Alkaline earth metal. Beryllium. So therefore, symbol will be BeF2. Right? Hagadre, can you tell me whether beryllium difluoride should have the net dipole moment or it should be 0? Yes or no? Net dipole moment of beryllium difluoride is 0. Yes or no? You can just send me yes, Y or N. Beryllium difluoride, whether it should have the dipole moment or it should be 0. Anyone? Okay, Sanjay, no. Anyone else? Okay, 0. Pooja is telling 0. Okay, very good. Both of you are correct. Net dipole moment of beryllium difluoride is 0 once again. All of you right, very good. Because beryllium, I gave a hint by telling that it is an alkaline earth metal. That means only 2 valence electrons for the beryllium. So each will be shared by fluorine. Okay? So therefore, there will be dipole moment in this direction towards the fluorine. Right? Since beryllium difluoride is having a linear structure, due to that, there will be equal and opposite dipole moment. So if you don't remember linear, no worry, but you should mention equal and opposite word. Since the net dipole moment is equal and opposite, therefore net dipole moment of beryllium difluoride will be 0. Net dipole moment of beryllium difluoride should be 0. All of you have understood? Any doubts? Okay. So that's where we have the beryllium difluoride, which is also having net dipole moment as 0. Now you should tell me, what about nitrogen trifluoride? whether it will have dipole moment or not. Nitrogen trifluoride. Okay, so I am talking about nitrogen trifluoride, NF3. Anyone? NF3. Whether it should have the dipole moment, yes or no? Whether it should have the dipole moment, yes or no? Rohan is telling it will have the dipole moment. Yes. Okay. All of you will agree with that? According to Rohan? Okay. Very good. Very good. Nitrogen belongs to group 15, 1,5. So it should have the 3 or 5 valence electron. In that, 5 they are involved in the bond formation, but 2, that is lone pair, will be left over. There will be leftover electron, lone pairs of electron. Okay? So therefore, there will be presence of net dipole moment. There will be presence of net dipole moment, no doubt. And please remember, lone pairs, those orbitals always they will move away from the atom due to their spinning action. They will be moving away from the atom. Therefore, upper arrow for lone pair orbitals. Okay? So nitrogen trifluoride will be having net dipole moment. It will not be zero. Please remember. So no need to about those values. What is that dipole moment? But you should remember that nitrogen trifluoride is having net dipole moment. It's not zero. Okay? Why nitrogen trifluoride is having net dipole moment? It's like boron trifluoride only. But still, boron trifluoride was having net dipole moment 0, but NF3 is having net dipole moment. What is the reason? The reason is due to presence of this lone pair of electron, NF3 will not form trigonal planar structure. Once again I will repeat, NF3 will not form trigonal planar structure as that of BF3. Since due to the presence of lone pair of electron on the nitrogen. So therefore, they will show the net dipole moment. Okay? All of you have understood? Now, I have the another molecule which is called as ammonia. Whether ammonia will have the similar structure as that of the NF3? Yes or no? Whether ammonia will have similar structure as that of NF3? Any one of you? Whether ammonia will have the similar structure as that of NF3? Okay. Rakesh? No. All of you will agree? Whether ammonia will have similar structure as that of NF3? According to Rakesh, no. They will not have similar structure. You can just mention yes or no. Okay, Rakesh, it will have the similar structure as that of NF3 because there also we have lone pair of electron because we are dealing with nitrogen, and there will be presence of 3 hydrogen in place of 3 fluorine. 3 hydrogens are present. Naturally, we will be having lone pair of electrons. Now, you should tell me among these bondings, net dipole moment will be towards nitrogen or towards hydrogen. You can just mention towards N or towards H. It's fine, Rakesh, it's fine. So, towards which element electrons will be moving? Towards nitrogen or hydrogen? You can just mention N or H. To which side electrons will be moving? Towards nitrogen or hydrogen? Okay, according to Sanjay, it is hydrogen. All of you will agree? All of you will agree with this one? Yes, Manjunath is correct. Sanjay, it should be towards nitrogen because if you recollect, in periodic classification I told nitrogen, oxygen, fluorine, chlorine, they are all electronegative elements. No one can come or no one can match to these elements: nitrogen, oxygen, chlorine, fluorine. But fluorine much more electronegative, no doubt. But even nitrogen, oxygen and chlorine, they are also electronegative. So therefore, since nitrogen is electronegative, dipole moment will be in this direction. Dipole moment will be in this direction. Now you should tell me, ಹಾಗಾದರೆ if I compare nitrogen trifluoride with ammonia, which will be having higher dipole moment? Nitrogen trifluoride or ammonia? Which will have the higher dipole moment? Any one of you? Which will have the higher dipole moment? Ammonia or NF3? You can just mention ammonia if it is higher value, or you can mention NF3. Okay, Shashank is telling NF3 is having higher dipole moment. All of you will agree? Okay, Sanjay is also telling NF3. But please remember, it is ammonia. Ammonia should have the higher dipole moment. Observe here carefully. It is going in opposite direction and it is in opposite direction. These three and this one, they are opposite. They are opposite, but here it is in the same direction. All of you getting understanding what I am telling? So therefore ammonia should have the higher dipole moment. Ammonia should have the higher dipole moment. Ammonia has the higher dipole moment. Okay, so what is the reason? The reason is dipole moment due to lone pair electron orbital and all the other covalent bonding is in the same direction, but here they are in the opposite direction. Fine, all of you have understood? So therefore ammonia will be having higher dipole moment. Okay, all of you have understood? Any doubts? So by this dipole moment is over. But these some of the examples which I have mentioned, they are present in your textbook also, in check sheet also. Go through that one. Okay, all of you have understood? Any doubts? ಹಾಗಾದರೆ when I am talking about water, water is having a bent structure. Anyway, in detail I will go in VSEPR theory tomorrow's class. It is having a bent structure. That is due to presence of two lone pairs of electron on the oxygen. Okay, imagine this is the reality of the water molecule structure. Imagine that there is no bend structure. Water is having a linear structure. Naturally, net dipole moment would have become 0. But here, net dipole moment is present because it is having a bend structure. Somewhere around 1.85 dBA units. It will be somewhere around 1 point. Value is not important. So it is 1.85 dBA units with respect to the water. But if water would have got a linear structure, net dipole moment would have become 0. Now, if net dipole moment would have become 0, then we would have not imagined the nature would have been like this. Now, how the water will be at room temperature? It will be a liquid. We will use that water for drinking purpose. Right? So that's where our 70% body cells or liquid is made up of water. Earth, 70% is water. If water would have been a linear structure, net dipole moment would have been 0, then the world would be in a different situation. In which situation, I don't know. I cannot explain. That is beyond my reach. But due to the bent structure of the water, due to the presence of dipole moment, we can imagine the world where water will be in liquid condition at room temperature. That is because when I am talking about this water molecules, delta positive, delta negative, due to the presence of partial positive charge, since hydrogen is attached to electronegative element, that is oxygen, so due to that, this water molecule can make the bonding with another water molecule. This is called as hydrogen bond. This is called as hydrogen bond. Same way, this hydrogen can make the bonding with another water molecule. This hydrogen can make the bonding with another water molecule because delta negative, delta negative, delta positive, delta negative, delta positive. Right? So that's where it is called as hydrogen bonds. Where, to be more specific, they are nothing but intermolecular. They are nothing but intermolecular hydrogen bond because they are present between the molecules, not within. They are present between the molecules. Therefore, it is a intermolecular hydrogen bond. It is not a covalent bond. It's a non-covalent interaction. Hydrogen bond is a non-covalent interaction. It's not a covalent bond. It's a weak interaction. Therefore, when I heat the water, these hydrogen bonds will broken. So, water molecule will become separate from each other. Therefore, they will become into gaseous form, vapor state. Got my point? In a liquid, these water molecules held together by intermolecular hydrogen bond. But when you supply the energy in the form of heat, now these water molecule will get separated due to the breaking of hydrogen bond. It's a weak interaction. So due to that, water molecule will be converted into vapor state. So therefore, dipole moment is also one of the factor to decide the physical state of a molecule. All of you have understood? So that's where we have the intermolecular hydrogen bond. Please remember this one. Hydrogen bond and all, it's a bit important. At the end of this chapter, I think Madam will be discussing this. So that's where we have the intermolecular hydrogen bond. Okay? So we will move to next one. Any doubts? All of you have understood? Rakesh, college, even I don't know, because no one is sure about the college. Okay? People are telling in the month of November and it may open, but we don't know when it will open. I think 2020 is meant to save our life. Okay, na? We have to accept it. No other way. But it may open, but I am not sure about. But any doubts in this? Okay? Fine. So that's where we have discussed about this one. Now I am talking about, once again I will come back to ionic compound because we have discussed about covalent compounds. Now we will come back to ionic compounds because tomorrow I want to keep only VSEPR theory. I want to finish it off, ionic compound. Okay? So what do you mean by ionic compound? So that's what I told. We have a very common example, sodium and chlorine. They will come together where sodium is going to donate the electron to chlorine. So therefore, sodium will become positively charged, chlorine will become negatively charged. Now if I take, this is the size of the atom. Okay, chlorine, naturally it is smaller size compared to sodium because sodium is alkali metal, chlorine is a halogen. One is on the extreme left, one is on the extreme right in the periodic table. So therefore, they have the huge difference in their atomic radius. All of you have understood? So now, once sodium has donated the electron, it has become smaller. Since chlorine has taken the electron, it will become larger. All these things we have already discussed. So that's where we have the cation, and that's where we have the anions. So chloride is an anion, Na plus is a cation. Any element which is going to lose the electron, then it will become a cation which will be smaller in size. Any element which is going to accept the electron, it will become an anion which will be larger in size. Any doubts in this particular thing, whatever I have written on the board? Any doubts? Any doubts? Okay. So, when I am talking about this process, with respect to sodium, I will tell this one as ionization enthalpy. I will tell this one as ionization enthalpy, which we have already discussed in periodic classification, delta IH. Ionization enthalpy with respect to sodium. With respect to chlorine, I will call it as electron gain. Electron gain enthalpy. Electron gain enthalpy. Right? So for an ionic compound to form, there are some of the deciding factors. Which are those deciding factors? One is ionization enthalpy and another one is electron gain enthalpy of the elements involved in the interaction. For ionic compounds to get formed, there are two major factors which are going to decide. One is ionization enthalpy and another one is electron gain enthalpy. These are the two major factors which is going to decide whether an ionic compound will be formed or it will not be formed. Okay? Now, observe it carefully. Whatever sodium and chloride ions are formed, now they are going to arrange themselves in such a way that they will form the crystal structure. They are going to form the crystal structure. They are going to form like a crystal structure. So this is where we have the sodium chloride crystal. This is where we have the sodium chloride crystal. So if I want to show as a crystal, it looks like, anyway, in detail, in second phases or this one, solid state you are going to discuss. That's where each intersecting points, I will mention them as Na plus chloride, Na plus chloride, Na plus chloride, Na plus chloride. So like that it will form. And those lines indicates the interaction, not covalent bond. Please remember, since we are dealing with ionic bond, there is no question of covalent bond. It will be the electrostatic interaction. It will be the multiple electrostatic interaction, which together called as ionic bonds. Multiple electrostatic interaction together, they are called as ionic bonds. Okay? Since it looks like a mesh, not mess, it looks like a mesh, right? So which we will be using as a filtering agent, right? So that's where mesh type of work. During the construction of building and all, you might have seen sand, they are going to filter through the mesh. Or mosquito should not come, so we have a net, mosquito net. That's where we have the mesh. So that mesh is nothing but lattice. So this arrangement is called as lattice structure. This arrangement is called as lattice structure. Lattice means a mesh type of structure. That's where it is called as a lattice structure. Therefore, once Na plus Cl minus will be formed, next step will be formation of this lattice structure. Formation of this lattice structure. All of you have understood? So therefore, formation of this lattice structure can be called as energy involved with respect to lattice formation. So therefore, it can be called as anyone. So therefore, it can be called as, it is involved, energy involved in the formation of lattice. So it can, shall I remove this one? It can be called as enthalpy of lattice formation. Enthalpy of lattice formation. Another important concept. Enthalpy of lattice formation. Enthalpy of lattice formation. So therefore, for ionic compounds to get formed, for ionic crystals to get formed, these three are the major factors which are going to decide. Which are those three factors? One is with respect to ionization enthalpy of an element. Next one is with respect to electron gain enthalpy of the element. And next one is enthalpy of lattice formation. All of you have understood? Enthalpy of lattice formation. Any doubts in this? Any doubts? Shall I move to the next one? Now, whatever sodium and chloride, multiple elements are present in a solid structure. So, whatever these elements are there, now we are going to separate those elements from each other. We are going to separate those elements from each other. That means we have to break these interactions. We are breaking these interactions. So if that is the case, whether there will be requirement of energy to separate these ions from each other, yes or no? So lattice means mesh. That's what I told Rakesh. Lattice means mesh, because all these ions, they will be arranged like this in a solid structure. Each corner point talks about the ions. One will be Na plus and another one will be chloride. So each these intersecting points, they are nothing but ions. And those lines indicates the electrostatic interaction. Since it looks like a mesh, therefore it is called as lattice. Lattice means mesh. Okay? It's a regular English term. Fine? So however, if I want to separate these ions from each other, whether it demands the energy? Yes. Yes, Rohan, it demands the energy. So that energy is called as lattice enthalpy. That energy is called as lattice enthalpy. So what do you mean by lattice enthalpy? It is the amount of energy required. It is the amount of energy required to separate the or to break the ionic solid, to convert the 1 mole of ionic solid into respective ions. So that's where we have the lattice enthalpy. What do you mean by lattice enthalpy? It is the amount of energy required to separate or to break the ionic 1 mole of ionic solid into its respective ions. So that's where it is called as lattice enthalpy. All of you have understood? Any doubts? So what do you mean by lattice enthalpy? It is the amount of energy to separate the ions of an ionic solid into individual ions. So that's where it is called as lattice enthalpy, just like bond enthalpy. Any doubts? Okay. So anyway, I will stop here. So tomorrow for 5 minutes we have to discuss about Fajan's rule related to ionic compound. Then we will go to VSE PR10. Okay. Fine. Any doubts? Okay then. Thank you. If you have any doubts, you can ask. Thank you. So practice, because day after tomorrow we will be having the exams. Okay? Thank you. Thank you. Take care. Bye. Okay, bye.